Thank you so much, Abhishek. Hello, everyone. I hope you're having a great day so far. And I'll be talking about some of the things that is considered as a good practice in industries. I'm Neil Ghosh. I'm a lead engineer in Salesforce. And today's talk is probably more relatable if you are a developer, because it will be something related to the day-to-day job you guys already do. With Abhishek's talks, you might have realized that more and more cloud vendors like Google is already realizing that it's so hard for customers to move their workload from on-premise to cloud because they have years of development already done. And on one go, you can't really lift and shift everything onto cloud or migrate it in any means. There is barely any luxury to rewrite everything from scratch either. So from a top view, it might seem that for an on-prem software, only the licensing fees that you have to pay to the vendor. But under the hood, you are paying for a lot of spaces and hardware that needs to go into their data center. You also need a team of skillful engineers to maintain it and patch and upgrade whatever comes on your way. However, in SaaS world, you might be paying a little bit of extra subscription fees, but you have no reason to invest a lot on your hardware or any of the software. However, in both cases, you do need customization because out of the box, the software may not work for you, but signing up and subscribing is as easy as signing up into Gmail. And you can stop at any point of time without long-term commitment, unless you do sign a commitment, long-term commitment with the SaaS vendor. So you might think as a developer, what is changing for me? It's only changing in the operational side. You still need to code, deploy, and write your business logic. But in recent days, the DevOps culture is kicking off. And if you see, there is an inner loop to development where you code, build, and do some unit testing, commit, and forget about it. And there's an outer loop of development, which mostly operation guys are taking care so far, which is getting into the continuous integration, deploying the software in various environments, and the QA team is there to test and release finally to production. But with DevOps, a same group of engineer is supposed to take care of end-to-end. So you not only code and build and test locally, but you also take care how to deploy it in production. In fact, you have to monitor the production workload as it being used by the end user. I mean, engineers do carry PagerDuty phones these days, don't they? And you can get a call to see that your workload is not writing well, and you have to rush to your office to fix it. But obviously, the ownership segregation is there, so you basically own a small part of the whole project, but you own end-to-end. So that's when microservice comes into picture. It has to be really broken down to smaller pieces so that smaller teams can take care of it. When you start developing in cloud, you have to make a choice which spectrum of serverlessness you want to be. One extreme spectrum is you want to control everything what you deploy and what you build on. Use something like Compute Engine, which is a virtual machine, and you have to maintain your OS, you have to patch and upgrade and everything. The other extreme is something very serverless like Cloud Function. All you need is to give a snippet of code, which will be run by your cloud vendor like Google and scaled. Somewhere in between, if you need a better packaging and better scaling without not much of effort, you can probably use Kubernetes, where you can bring your tech stack, you can bring your container, and then let Kubernetes scale for you. App Engine is a really great choice if you have a great bunch of developers and you don't really invest a lot on the infrastructure layer. Then you can just develop in your own stack and deploy to App Engine. It'll scale as per the request. Cloud Run, if your workload is stateless and exposing an HTTP endpoint, you can just give it to Cloud Run. And as opposed to Cloud Function, Cloud Run, you could use any container you want. So that basically opens up all the tech stack for you. The fundamental scaling construct in cloud is horizontal scaling, as opposed to vertical scaling where you have to upgrade the same machine and server, upgrade your RAM or CPU. In horizontal scaling, you can use smaller computers, but many of them, and your load balancer can route your traffic intelligently, whatever server is free at that point of time. Imagine if you have a higher load coming in for a day of the week, or there is a sale going on, then it can automatically spin up more and more instances and share the same traffic that is coming from the public. The one thing you need to be really taking care that if the services are big, then the scale time is increasing. So if you have a stateless service, you might want to have the startup time smaller and smaller so that you can scale rapidly. And if you know that there is a point of time in the year, for example, a Christmas sale or a weekend that where the traffic is supposed to come, you can predictively set and provision that, hey, can this be automatically increased? Can the number of instances be automatically increased when this traffic is about to be coming, so that you don't have to scale on demand? But what about persistence layer? When it comes to databases, you have only single database probably backing all the application server. In that case, all the traffic might actually get into the bottleneck of database. And finally, your database crashes, although you keep on adding application servers. So how do we scale database? For a RDBMS like MySQL, Google gives you Cloud SQL, which is a completely managed MySQL. You could always have multiple read replicas. Read replicas are nothing but slaves in master-slave architecture, where it is always in sync with the data of the master. And you can actually redirect all your reads to the slave instances, and you can have as many as slave instances you want. And if your read throughput is required to be a lot, then you can more read replicas. And if your write requirement is low, it can always go to the master, and as soon as things are changing, it is replicated to the slave. However, if you see master is a single node database, and it is handling all the writes. What if the master fails? So Google Cloud SQL gives you failover instances, which is always in sync with master and can take over the writes as soon as the master is starting to not responding or it goes down for some reason. So read and write concerns can be segregated, like a CQRS pattern, which is commonly used in the industry, and the application can be made highly available. Now, if you, from the last slide, you realize master is again a single point of failure. What about your write throughput is a lot? So your application is write heavy. Then you probably want to have multiple masters. In that case, you probably want to partition your total data set into multiple master with some kind of consistent hashing of a key. For example, if your user IDs are auto-generated, then probably distributing them across the number of instances is a good idea. And you can have multiple shards, and your application layers figures out from the user ID which shard it needs to go to. One can also do organization or tenant-based sharding. For example, you have new customers getting on board, you can actually dedicate them new shards. So your application logic or a configuration server like Zookeeper or runtime config can actually intelligently tell that, hey, for this tenant ID, I need to really go to this database. And if there are bigger organization, bigger customer, you can dedicate a single server. If there are multiple small organization, you can club them together to a server. In this case, adding new server is not a problem. But if you're sharding based on user ID, probably rebalancing the data which is existing in 3 server into 4 server is a problem for you. In that case, you probably want to go for something on NoSQL side of it. The NoSQL got popularity because it could dynamically scale horizontally based on your workload as time goes on. So data store is a Google's cloud platform's NoSQL. It was introduced long back when App Engine was introduced. It's one of the first investment of Google Cloud Platform. is a document-based database, and it is fully managed. So what you pay is basically what you use. You don't have to really provision anything in the data store side. So although it's NoSQL, it does give you some of the SQL constructs like GQL, limited amount of queries. It also gives you atomic transaction and consistency to some degree. But you don't really have the SQL joins that you usually do in RDBMS. You can also query by some of the attributes, which is not a primary key, but the index, making an index out of that could be tricky, and it could slow down your application. Since it's a distributed database, you don't really have any predictive latency, but if you provision it for strong consistency, it can guarantee you data being replicated at real time to different servers. So Google Cloud Spanner basically combines both the good things from both the world, SQL, RDBMS, and Google Cloud Data Store, the NoSQL. It pretty much guarantees that your data is consistent, and also it gives you all the SQL construct that you are already familiar with in RDBMS. This is a breakthrough technology, and I think inspired by Google Spanner's paper, CockroachDB is an open source version of it that you can go and try out as well. If you're a financial institution, for example, for which your latency, consistency, and also querying with standard SQL is important, Google Cloud Spanner probably is a good choice for you. Now, by introducing caching, you can always protect your database from high read-write, because sometimes there are repetitive data that needs to be queried by application server, which you don't really want to read from database every time. So you might want to introduce a caching layer in between. Google App Engine had Memcache. Google App Engine Standard had Memcache from long time. It's a distributed cache with key value pair. So not all your data read-write might have to go to the data store. If you have something repeating, you can always return from cache in sub-millisecond latency. So what about the data changes? Then the cache becomes stale. So you might want to use a write-through technology so that it actually writes the latest value to the cache and then writes to a database. If you're using Kubernetes, Google App Engine Flex, or Cloud Run, whatever, you might want to use Cloud Memory Store, which is a fully managed Redis instance provided by Google Cloud Service. And that has all the feature Redis has, and is really performant when it comes to reading key value pairs. So for example, using Spring Data Cloud, you could use the write-through cache and implement like this. I have a function called save profiles, which is basically a write function. And every time there is a profile object coming to this function, it makes sure that it is stored in a cache with a cache put annotation given by Spring. It will be stored with a prefix name and the actual name as the second part of the key. And then whenever there is a read operation happening, for example, find by name is a read function, and the cacheable notation makes sure before even going to database, it actually consults the cache with the key prefixed by name and the name it is trying to read from. So in that case, probably most of the time, it is not going to have to go to database at all. It can return from the cache, and there probably is a 10 times performance gain you can see. And in the right side, you can see using a Redis client how you can actually read, actually inspect the keys that are already stored. In case you delete or you set a time to leave for the memcache keys, that means it will automatically expire, and you have a read call coming in, it doesn't find it, then it's a cache miss scenario. Then it will go to the database and hydrate the cache, and then return to the customer. And for the subsequent calls, you will have the data available. So this is an interesting code. You can probably take a screenshot and probably read through later. Whenever cache invalidation and naming things and off by one error. And I said, there are only two hard things. Now let's get into multi-tenancy. So to achieve multi-tenancy, your application really doesn't have to be multi-tenant. You can have multiple single-tenant application deployed catering to your different customers. In that case, you're basically sharing your artifacts. Your artifacts are nothing but jars and wars that is getting built from your code, from your source control system. But in case of true multi-tenant system, you're also sharing the resources. You're sharing your same server, compute, and database to different tenants. And in that case, you probably have to make sure your data is super isolated from different tenants, because your tenants or organization or customers should not be really aware of other customers that are being hosted from the same server. So multiple single tenant infrastructure is very useful when you want to have a feature parity. For example, you have a new version of your app getting rolled out, and you want to only roll out for specific customers, then you probably roll out in those virtual machines or whatever database that those customers are using. But this also can be achieved in a multi-tenant scenario with some kind of kill switches, something like launch darkly or runtime config, where the application intelligently figures out, hey, if the tenant IJ is this, then only I need to serve this part of the code that you have to bake in the application logic. And when it comes to customization also, the single multi-tenant architecture is very useful, because you are letting you're letting your application developers to write code specific to a customer. But what is most useful in the multi-tenant scenario is elasticity. For example, you have two customers. One is not really using the system a lot, and the other one is really want to use the system every day and night. Then the resources, there is no dedicated resources per tenant. You can always see as a combined read or write call, and if it is getting fulfilled by your total infrastructure. There is no boundary that one customer can use only X number of VMs. So in that case, you could do cost optimization, because not all your customers are using as a heavy read-write at any point of time. But you really need to have a good architecture for data isolation. So one of the typical scenario in RDBMS world people use is they use schema per tenant. For example, for different tenants, you can have different databases created within the single server. And every time there is a tenant that is getting onboarded, you can create those databases. And every database which is catering to different tenant might have their own copy of the tables, and the tables would be very analogous to each other. In that case, though, there is a certain problem that might arise. Let's say you are upgrading your database, then you have to upgrade all such schemas individually. There is no single command that is going to work for you. So you need to take care of the scenario when some of them are upgraded and some of them are not upgraded. But there is another approach that a lot of cloud vendors and SaaS application providers use, is maintain a tenant ID column. In that case, you have a dedicated column tenant ID, which is basically telling which tenant this record belongs to. So whenever you do a query, the tenant ID filter has to be inherently a part of the query. So you probably don't want to leave it to the developer. You might want to abstract the class, for example, a repository class which is talking to your database, that will always have a tenant ID, where tenant ID equal to your tenant company name at the parent level. Or you can also create different views whose query actually says that whatever is the current tenant ID in the session, I want to only see those data. But the problem with this approach might be your database, your single table grows very large, and your indexes similarly goes very large, and your queries start to slow down. In case of different databases, different schemas, you have only the data for the company being queried at any point of time. So in MySQL, databases are analogous to schema. You can always use different schema for different databases for different company. In Postgre world, schemas are inside databases, and that's just a logical partition. So you can use them for different customer. In data store, which is NoSQL by Google, you can use namespaces so that you don't have to maintain a table for every customer. The namespace is a logical partition at the root level, and your entities can reside inside that. Similarly, when it comes to caching, you can choose your keys intelligently so that your tenant ID is prefixed with the cache, and every time there's a read and write, you have to add the prefix so that you get correct company's data. Google Cloud Storage also gives a construct bucket. You can dedicate one bucket for tenant and have their files inside it, the hierarchy of the files. Even in BigQuery, which I didn't discuss at all so far, they have something called data sets within which tables are stored. You can dedicate one data set for every tenant. So how do you decide which request belongs to which tenant? So authorization is really, really important for this. Whenever there's a request coming from outside world, the first thing you might want to check is some kind of token, JOT token or bearer token, and want to really validate which tenant it is trying to pretending to be. The tenant ID can be embedded in the token, and once you figure out the tenant ID, you can probably store it in the further request lifecycle as a global variable, for example, thread local in Java, so that every time there is a read-write call or any kind of decision-making further down the request scope, you have the tenant ID handy instead of having to pass that tenant ID into every function call as an argument. So when it comes to Google Cloud Platform, you have cloud identities with IAM policy. You can decide which developer can access which resources, and also you can create groups so that you can set a policy for a set of developers. For example, you want to restrict the production access, then you might want to create a different group for production and give them read-only access only. Service accounts are something for service-to-service communication. So every time there's two services communicating within your cloud, it doesn't have to be a real user. It can have a service account, and it can have a pre-authorized policy, how much it can talk to. Signed URL is very handy when you're uploading big file to Google Cloud Storage. So whenever you have a signed URL created, it already have the authorization baked in if that can be invoked by a specific tenant or not, and it can be short-lived as well. So when you create a SaaS application, you need probably two management service. One is probably an onboarding service when a person from your company will provision a new tenant, and then you hand over to an administrator within your customer who can add other users to that tenant, and they can control what can be done within the context of the tenant. And you as a super admin sitting at the SaaS provider can control what are the tenants that are active right now and who should have access. So as I said during one of my first slides, that you as an engineer are no more only application developer who writes your code, throws into the other side of the wall, and the ops guy picks up and deploys it for you. You are now, the line between the ops and the developer is blurring. So you are owner for the end-to-end. So monitoring the application, how it is performing live, and to get the telemetry is now up to you. So while developing itself, you might want to add some instrumentation to your code so that it emits metrics at the runtime. So OpenTelemetry is a project within which you have open sensors as well, and it's a very, very handy tool for instrumenting your code. So if you see, you can, at the left bottom, you have a graph for tracing. Trace is nothing but a span of A multiple span, it's usually a life cycle of a request. For example, somebody is trying to get a message endpoint called. So the whole message endpoint might be talking to multiple other services. For example, it can first thing authorize, it might spend time on trying to get the cached value, and it might miss a cache, and then it might go actually do a MySQL query with database, and then generate a response and return to the response. So if you want to really have control of what is happening and debug issues, for example, which is taking more time, then this is a nice chart to have. So you can basically zero down on, hey, MySQL query seems to be by most expensive span, so let me optimize that part, or let me talk to the team who takes care of that. So OpenCensus is open source, and it can have multiple data sync. So Stackdriver is one of the Google's data sync that is supported by OpenCensus. Similarly, you can have Prometheus or Zipkin, which can actually take the metrics aggregated by metrics emitted by OpenCensus and display in a nice manner. The other kind of metrics that you want to emit is probably some kind of gauge or time series data. For example, in your application, you want to know how many people are logging in per hour, or how many people are really invoking this method in last 30 days. So you might want to emit a metrics every time there is a login. And since there will be huge amount of traffic, you might want to sample that as well. For example, in every 100 login, send one metrics, so that you want to know average latency that needs to be calculated. So StatsD is a service that you can run in each of your hosts, and your application server basically talks to the local host and emits the metrics, and StatsD sends it as per sampling, and aggregates it and sends it to further metrics aggregator, something like Graphite or Grafana. So Datadog is one of the tools that uses StatsD for that. So monitoring is really, really important in that scenario. So that is pretty much all I had. And if you have some questions regarding this, which is burning in your mind, you can get in touch with me, tweet or whatever, email, and I'll be trying my best to respond to all of you. Next up, I'll try to I'll invite Shantakumar Mani, who is an expert GCP trainer, and he will have some very cool sessions for you rest of the day, probably 3 hours or so. And I hope you will have a productive day today.